Hello everyone, welcome to my presentation. My name is Yan Xia and I'm a PhD student in the chair of Photogrammetry and Remote Sensing at the Technical University of Munich. Today, the topic of my presentation is completion of sparse and partial point clouds of vehicles using a novel end-to-end network. The co-authors in this work include Wei Quanliu, Zhipeng Luo, Yusheng Xu, and Professor Wei Stilla. This work is also supported with Xiamen University. Let's start. 3D point clouds acquired from mobile laser scanning systems deliver detailed 3D information of road scenes during the driving. However, acquired 3D point clouds of vehicles from MIS systems are incomplete due to the object occlusion or self-occlusion. For instance, from this image, we can see the raw data from MIS systems has some typical characteristics. On the one hand, the point cloud is sparse. On the other hand, there are large percentages of missing points. Thus, this kind of point cloud is useless for downstream tasks, such as recalculation and detection tasks. Therefore, we would like to have a way to infer the complete 3D geometry of objects from this incomplete sensor data. This problem is known as shape completion. Completing these partial point clouds can be beneficial for instance extraction, type classification, track estimation, and identification of vehicle model tasks. Especially, completing geometric shapes of vehicles plays an important role in autonomous driving field. For example, if we fit the bounding box to be the segmented cars in this scan, the front of some cars would be missing due to occlusion. As a result, a self-driving car navigating in these environments may not know the full extent of these obstacles. But if we can complete these vehicles, knowing the full extent of these obstacles will help navigating. To address these problems, we propose a novel end-to-end network called sparse to uniform S2U-Net to complete these sparse and partial point clouds. Different from other completion networks, we adopt a upsampling strategy to output more uniform point clouds. It's divided into two modules, encode and decode. The encode extracts global features from the input sparse and partial point cloud, and then the decode generates the uniform and complete point cloud based on the extracted global features. Here, we give the details of the network architecture. Our encode is based on point net. In the encode, the n times 3 input point cloud is passed through the first point net layer to learn a future f1, and then we concatenate the f1 with per independent point future p1 to obtain the aggregated futures. Next, we fit the aggregated futures to second point layer to get the final global future f2. In the decode, we explore a cost-to-fine training approach for generating the complete point clouds. The 3 for collection layers are used to generate a coarse but complete point cloud. Then we use the up-down-up expansion unit to generate the dense point clouds. Lastly, we use the farthest sampling step to output the final point cloud with fixed points. For the generated point clouds and the ground truth point clouds, we expect their topological distance to be the smallest. There are a few common distance metrics. The popular choice is the chamfer distance. Each point finds its nearest neighbor in the other set. If you take the mean over all nearest neighbor distance, you get the chamfer distance. It's more robust to outer layers. The second metric is a smooth distance. Here you solve an optimization problem and find the minimal cost to transport one set of points to the other set. In this work, the loss function involved two terms since we employ a cost-to-fine training method, where P-cost is the sparse point clouds from the decoder. The PGT prime is the subsampled ground truth point cloud with the equal size as P-cost. The second term is the chamfer distance between the final predict point clouds P-fine and the for ground truth point cloud PGT in which gamma is the hyperparameter to balance the relation of them. Next, we conduct the experience on the two real-scan data. The first one is TUM-PF 2016 dataset, which provides dense and aggregated point clouds, but there are no ground truths. Another one is KITTI, which provides sparse single-frame data. The baseline we choose is VPC-Net, which is the first point cloud completion network using raw point clouds directly. Comparing the results in KITTI dataset generated by S2U-Net and VPC-Net, we can observe that S2U-Net can produce more uniform point clouds, while VPC-Net fails to recover such structures. For the raw point clouds from TUM-PF 2016 dataset, S2U-Net produces dense and complete point clouds from most partial inputs. However, from the second row, we can see that generated point clouds cannot keep fine-grained details. Besides, the last two rows show examples of failing cases. We can clearly see the generated points are not lying on the surface, with many points escaped it. To further improve the quantity of the complete point clouds, recently we proposed an improved method called VPC-Net. The aim of VPC-Net is to refine the complete point clouds with fine-grained details. There are three major improvements. The first one is to complete the missing surface with fine-grained structures. Second, it can preserve the origin details of the inputs. At the same time, it also produces uniform point clouds. More details of VPC-Net, please refer to our new manuscript. We submitted it to the Journal of ISPRS and archive. Different from S2U-Net, it consists of three modules: encode, decode, and refiner. We improve the encoder to better extract global features, and then using the multi-stage decoder to generate the dense point clouds. Following by the refiner, it can refine the complete outputs from decoder to be with fine-grained details. Also, we give the results using KITTI dataset. The first row is 5 detected vehicle examples in a single frame. The second row shows these partial point clouds. The result generated by VPC-Net includes the details of the missing parts, and all points are more evenly distributed on the geometric surface, while many points from the VPC-Net escaped the cut surface, which can be observed in example 3, in example 4, and example 5. Unlike point clouds from the KITTI dataset, point clouds from TUM-PF 2016 dataset are very dense. In spite of this, VPC-Net can still generate detailed information, not only the partial inputs, but also for the missing structures. This video is to illustrate our work can be applied to real-time applications like 3D detection tasks. The top is vehicle detection from raw real-scan data. We can see the point clouds of vehicles, the blue one, in the gradient bounding box are very sparse and incomplete. The bottom one is the vehicles are detected and completed at the same time. This video is to show our completion method can be applied to 3D traffic monitoring tasks. We use one wide line rotating 3D laser scanner on the center of crossroads to collect the spatially dense and accurate 3D information at the crossroads. Then, the typical monitoring method SNAM is used to estimate the vehicles in a 3D map. The velocity, orientation, and trajectory of vehicles can be obtained using SNAM method. However, it cannot reconstruct the complete shapes of moving vehicles. Thus, we can use our method to complete these vehicles. If you want to do the similar work for publication, you can find the data here. That's all for my presentation. Thanks a lot for your listening and attention.